The limit of a function. What is a limit? I know you heard this. So we've got three functions, f of x, g of x, and h of x. We got a table of values, and we are looking for taking x values closing in on 2, 1.8, 1.9, 1.99, 1.999, etc. And then on the other side, 2.001, etc. Right? And we can see what's happening with these values. And what we are asking ourselves is, if you examine the columns of table X, you'll note that for the upper set of values, as you go from top to bottom, the values are increasing and getting close to the number 2. For the lower set of values, as you go from the bottom to the top, so 2.2, 2.1, etc., the values are decreasing. And getting closer to the number 2. We say that the x values are approaching 2 and express this as x approaches 2. It's x and then the arrow, but that's red. It's x approaches 2. Examine the columns of f of x, g of x, and h of x. Complete the following statements. As x approaches 2, f of x approaches. Say it out loud so that the audience can hear you. 3! Thank you. I think it's reasonably sensitive. It might not be. For h of x, or sorry, g of x, the values approach 1. And for h of x, the values approach
infinity and beyond.
Infinity and beyond. Although there are just different infinities, but as Cantor first postulated and then proved. We say the limit of f of x as x approaches 2 is equal to 3. We can also say the limit of, and then name the function, x squared minus 2x plus 3 as x approaches 2 is equal to 3. These statements can be expressed mathematically. So exactly how this is read, that's how it's written. The limit as x approaches 2 of f of x equals 3, or the limit as x approaches 2 of x squared minus 2x plus 3 is equal to 3. Complete the following statements for g of x. So you're just going to write out the words, right? So what's it going to be? The limit of g of x as x approaches 2 is equal to what? What was it equal to?
1. Drop the page.
1. Okay, and mathematically, right, the limit as x approaches 2 of the function g of x is equal to 1. Or, what was g of x? X squared minus 3 equals 2. The limit as x approaches 2. Short-term memory. So we got x squared minus 3x plus 2 over x minus 2 equals 1. Now, I've gone to the horrendous trouble of graphing these things. So this is x squared minus 2x plus 3, right? That's the first one. And we want the limit as x approaches 2, so I think we can pull up points. So you notice x is getting close to 2, and you know we actually have the point 2, 3, right? Like it actually exists, and we have the point 2, 3. Right? Okay, this is the second graph, x squared minus 3x plus 2 over x minus 2. And we can see, okay, come on. And we want x. So as x approaches 2, where are we? What's at 2? It's undefined. But as it approaches, so what are we coming close to, right? We're coming close to 1, and coming down from the other side, we're getting close to 1. So, this, have you ever seen this? This is Desmos. Desmos.com. Right? It's the coolest graphic thing, right? So you can't use graphic calculators, but if you're at home, you can go to Desmos.com, you can graph these things and you can play with them, right? And it's just nice, it's got a nice grid, it's labeled, you know, 0 to whatever, and that you can move it around, and you can look at the different functions. You can drag along it. We can see we got 2 and it was undefined. And then what else do we have? We had H. We have H. And as we approach 2, what's going on? Well, we're climbing, right? So there's the infinity and beyond, not beyond. In general, we write the limit as x approaches a of f of x is equal to L, and say exactly that. If we can make the values of f of x, okay, we can say that if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a but not equal to a, right? So in f of x and g of x, you can't have x equal to a. You can't have x equal to 2. In f of x, you can. It's defined, it exists there. But in the other two, it doesn't exist there, right, for whatever reason. If you go on, which you're likely to, I mean, nobody takes calculus because they're not going on, and do another calculus course in university, you may get into the formal definition of limit, which if you're interested, you can look up something called the epsilon delta, okay, the epsilon delta, or you can just leave it for next year, right? But there's a more formal definition, but it just says we can get as close to L as we want by getting as close to as close to A as we want. Okay, and then there's a whole body of stuff, but that would be the proof. Okay, we're not proving it; it is. Okay, what's next? No. I'm missing. Oh, determine each of the following. Here we go. All right, so we've got 3 functions. Determine each of the following. F of 2. Okay, so f of 2 is, well, wherever you see an x, substitute 2. And that's equal to 3. Okay, cool. Huh? G of 2. So that's 4 minus 6 plus 2 over 0. So G of 2 is 0 divided by 0. And what's H of 2? Oops, I want x to be 2. And that's 3 over 0. And 3 different situations arose. F of 2 exists. So the limit of f of 2 exists, and the limit as x approaches 2 of f of x is equal to f of 2, right? So this exists, right? There was the point, 2, 3. It's on the graph, right? So the limit exists, and the limit is just the value of the function at that particular point. G of 2 does not exist, right? G of 2 is 0 over 0. But the limit of g of x does exist. We did find the limit. H of 2 does not exist, and the limit as x approaches 2 of h of x also does not exist, right? There is no limit. Let's examine the graphs of these functions to gain a better understanding of, okay, been there, done that. Right, we just did those. So what did they look like? It was, okay, and then, that was 2, that was 3, and there was a point there, right? That was a point. And in the other one, so remember that when we sketched along it, we came to the point 2 undefined. But as we got close to it, right? It was, oh wait, it was 1, wasn't it? That's a 1. As we got closer to 1, and then there's a hole in the graph, right? Which is called a point discontinuity, right? And it's point, so you can't see it because it's a point, and points have no dimension, right? But if you trace along it, that's what I like about decimals, right? When you hit it, it says undefined, and you go, oh, I didn't see that, right? Because you can't see anything that small, but it's there, okay? Or well, it's not there, right? It's point discontinuity. And then this guy we had. Right, and this was 2. So those were the graphs. Right. Got ahead of myself. We already did that, but there it is. Right. Any questions about those? Right. And you can examine them yourself. Right. So the graph of f of x is a continuous curve. All the points are connected together. The graph of g of x is a line with the point 2, 1 missing. The graph is almost, but not quite continuous, right? You'd have to lift your pen and then move it over and put it back down. In fact, we say that y equals g of x has a point discontinuity.
So if it's always continuous, why is there a limit for f of x?
Well, it's just the limit as x approaches 2. So we say as x approaches 2, what's f of x? And so we see it exists, right?
Yeah.
And we said f of x, f of 2 exists. So you
can
can do that. You can just say, what's the limit as you're approaching 2 of this particular value? As well, it's 3, and it actually exists.
Okay, so you can do it with any point then?
Yeah.
Okay, okay.
The graph of h of x equals 3 over x minus 2 squared is not continuous at x equals 2. In fact, it has an asymptote. So make sure you can distinguish between an asymptote and a hole in the graph. Right? Good to go. Good to go. Now you can see this. Determining limits given the graph of a function. Use the graph of y equals f of x below to state the following limits. Okay, the limit as x approaches -3. So here's -3. What's the limit? What did we say it was on the stuff you can see right above? Infinity. Or we're going to say it does not exist. Which we may abbreviate as DNE, does not exist. But you're also right, it is also what? Infinity. So
we should set both answers for that? Or?
Yes, for the first unit. Good point. So let's take a look at this. This is out of the Stewart Calculus book for university. Right? So you're not going to find this, I don't think you're going to find this in your books. It talks about infinite limits, right? It says, find the limit as x approaches 0 of 1 over x squared if it exists. Okay, so what's going to happen, right? 0, you're going to be dividing by 0. Right? As x becomes close to 0, x squared also becomes close to 0, and 1 over x squared becomes very large. Table. 1 billion. In fact, it appears from the graph of the function, that graph of function, table, graph, that the values of x can be made arbitrarily large by taking x close enough to 0, right? You throw x as 0.00001, you get 10 million, right? Or whatever. Thus, the values of f of x do not approach a number, so the limit as x approaches 0 of 1 over x squared does not exist, right? That's what your book's going to say in the limit section. However, to indicate the kind of behavior example, we use this notation. The limit as x approaches 0 of 1 over x squared is equal to infinity. This does not mean that we are regarding infinity as a number, nor does it mean that the limit exists, right? It doesn't. It simply expresses that the particular way in which this limit does not exist. 1 over x squared can be made as large as we like by taking x close enough to 0. In general, we write symbolically the limit as x approaches a of f of x is equal to infinity to indicate that the values of f of x tend to become larger and larger or increase without bound as x becomes closer and closer to a. Okay? So you can say does not exist, and you can say infinity for this one. Okay? So let's move back. The limit as x approaches 0 of f of x. So where's 0 on here? Must be. Is what?
2.6.
Sure. Let's go with 2.5. Just round. And it's continuous, right? So yeah, we could take the limit as we approach something even if it is continuous at that point. But the limit as x approaches 3 of f of x is what? Okay, wait. What's the open circle mean?
What? Discontinuity.
Yeah, so does not include. What's the closed circle mean? Do include, yes. Okay, so what is the limit as x approaches 3 of f of x?
5.
5. Okay. So think about it, right? You're not at 3, right? When we say limit as x approaches, you are never getting to 3. But you can get as close as you can. Now, when you get as close as you can to 3 on here, what's the value? 5. Okay, everybody got that? Key point. Huh? Key point. It's not 1, right? F of 3 is 1. But when you do the limit, you are never at the point. You are as close to the point as you want to get. And you will be getting closer to the value 5, no matter which way you're going, right? Whether we are approaching from below or approaching from above. Okay, we're still getting to 5. Now, left and right-sided limits. It's possible for a graph to have 2 different limits as x approaches a particular value. For example, in the graph shown below, the limit of f of x as x approaches 2 from the left is different from the limit of f of x as x approaches 2 from the right. Okay, so approaching from the left, approaching from the right. The limit of f of x as x approaches 2 from the left is -3. But the limit of f of x as x approaches 2 from the right is 1. Using limit notation, there it is. Since the limit of f of x as x approaches 2 from the left is not equal to the limit of f of x as x approaches 2 from the right, we say the limit of f of x as x approaches 2 does not exist. And this is the time where you actually use does not exist. And it must be, right? You can't say infinity or whatever. Okay? So this is not one of those optional, it doesn't exist, but it's infinity. This is one of those, it does not exist. Since the limit as x approaches 2 from below, so this is from the left, or I would say just from below, from the left or from below, this is x approaches 2, so from the negative side, right? Coming from negative to positive, this is going from the right or to the left, from the right to the left, or from above. That's this notation. These limits are not equal to each other, then we say the limit does not exist. Okay? In other words, the left side limit, the right side limit must be the same for it to exist. So here, that happened, right? As we come from the left, as we come from the right, you're getting the same number. Okay, question? If you have questions, throw them. Exercises. The equations of 4 functions and their corresponding graphs are shown below. State the points of discontinuity of the functions, the equations of the horizontal and vertical asymptotes of the functions, and the limits of the functions as x approaches indicated values. Okay, so here's the first function. 2x plus the root of x plus 1 minus 1 over x. So is there a point of discontinuity? Where? 0. Okay, so let's go here. And if I graph this right, okay, so there's the graph, right? And you're saying 0. And it looks like you're right. What value are we approaching at 0? It's getting close to what? 2.5, right? Okay, so what is the point of discontinuity? It is the point 0, 2.5, right? Or 5 halves. Let's change it up. We'll call it 5 halves. Are there any asymptotes here? Yeah. What? y equals 2. So there's a horizontal asymptote, y equals 2. Okay, and now we're going to do 16 different limits. Sorry, 8 different limits. So what is the limit? Now, we're doing one side, right? What is the limit as x approaches 0 from above or from the right? 2.5. Now we'll say 2.5. I'm going to go 5 halves. Let's be consistent. What is the limit as x approaches 0 from below or from the left? Same, 5 halves. So what is the limit as x approaches 0 of f of x? Still going to say 5 halves. Why? Why does this exist? Because the left-sided limit and the right-sided limit are the same. So then the limit exists. What's the limit as x approaches infinity of f of x? 2, right? As we go out, we're coming down to the asymptote, right? What is the limit as x approaches -1 from the positive side? Since we're going this way, approaching -1. 3. What is the limit as we approach -1 from below or from the left? There isn't one. Does not exist. So then what do we say about the limit as x approaches -1? We got one-sided. What's the limit as x approaches -1? What do these two have to be for this to, so it doesn't exist? What is the limit as x approaches -infinity of f of x? Does not exist. Doesn't get there, right? I mean, you can only go down to -1. So there ain't no curve out there. Okay. Is there a point discontinuity here? Yes. And where might it be? Where's it at? Okay, so let's check. What values are we approaching? -1. What happens at 2? And 5, right? Okay. Cool. I like this. Sliced bread has nothing. Actually, this is better for you than sliced bread. Point of discontinuity was what? 2, -1. Any asymptotes? Okay, the limit as x approaches 2 from above, right? So from like 3 going down to 2 is? The limit as x approaches 2 from below, so climbing up to 2, right? Like 1.9, 1.999 is? And so the limit as x approaches 2 is -1. Limit as x approaches infinity is? Well, where's it going to?
Infinity.
Which infinity?
The right infinity.
What's down here?
1 and 4.
Yeah. What's down here? Which infinity? -infinity. What's up here? Right. So this is -infinity, and as x approaches -infinity, we're going to infinity, positive infinity. Which doesn't need a sign. Show me a sign. No, you don't need a sign. Okay, next. X cubed -1 over x squared. Okay. So is there a point of discontinuity? Let's take another look. Expand. Oh, draw lines. Okay, there it is. Think there's a point discontinuity? Where?
0 and -1.
That's not a point discontinuity, though, right? Point discontinuity is this, right? It's a hole. It's a break in the graph. Okay, points of discontinuity, none. Equation of asymptotes. X equals 0. What else? I'm going to go with y equals x. X equals y. Okay, that's called a slant asymptote. Probably the last time we heard that word. Not asymptote, but slant asymptote. Okay. You can do that. You can look that up if you like. Okay, so you can see it, right? So, I mean, what is the limit as x approaches 0 from the right? So going from 0 from above. So going this way. Negative infinity, right? I mean, we might as well say, and here's the reason we say it, right? You could also say it does not exist, you get the mark, but when we get into curve sketching, which is one of our units down the road, it's kind of nice to know where it's going, right? So if you say, oh, well, this one goes, you've seen asymptotes that do this, right? Like one goes up, one goes down. So it's really helpful to know that, hey, this one's going to positive infinity, this one's going to negative infinity, so when I go to sketch it, I can say, oh, yeah, that's, as opposed to just saying it does not exist, right? Which says what? Now I got to figure out which way it's going. Okay, so we just figure out which way it's going. So my preference is, and I think it's something you should get into, if there is a limit, like positive infinity or negative infinity, state it that way. And when it truly doesn't exist, right, because the one-sided limits aren't the same, that's the place where you should say does not exist. Keep in mind your book, however, is just going to say does not exist. Okay? All right, so what did we say it was? Negative infinity. And the limit as x approaches 0 from the left is? Negative infinity. And so the limit as x approaches 0 is? Right? If the two one-sided limits are the same, then that's the limit. The limit as x approaches infinity of f of x is? Remember, x equals y, or y equals x. So as x approaches infinity, then it's got to be infinity, right? And as x approaches negative infinity, I got to look again. Oh, okay, what is it? So you're going this way? It's going to be negative infinity. Thank you. You say it out loud. Okay, so far so good? All right, any point discontinuities?
No, I know you use it.
Yes. Where is it? 2, negative 1. All right, hey, let's check that out. Which one is this? Do you know how long it took to type these in? Okay. So, somebody said there's 1 and 2, negative 1. Yeah. So 2, undefined, right? What are we approaching? Negative 1. Cool. So, point of discontinuity is 2, negative 1. Asymptotes. X equals 1 and y equals 0. Okay, limits. The limit as x approaches 2 from above.
-1.
Thank you. There's a point discontinuity there. And as x approaches 2 from below. And then just in general, as x approaches 2. Thank you, you're catching on. The limit as x approaches 1 from above. So as we're going 2 down to 1, what's it doing? Yeah, I'm not doing does not exist, sorry. Negative infinity. The limit as x approaches 1 from below, as we're climbing up to 1. Infinity. And the limit as x approaches 1 does not exist, right? This is the time we really want to use, well, you have to. You can't say anything here, right? I mean, you can say an answer which is wrong, but if you want an answer which is not wrong or right. And the limit as x approaches infinity of f of x, and is negative infinity of f of x, 0. And you can't combine these two, or this is an infinity from below. As we approach infinity from below, what? We can do that, we can't approach infinity from above.
All right, so when you have limit f of x approaches 1 from the right, wouldn't it be positive infinity? I'm just confused about that.
Approaches 1 from, okay, wait, did I write this out wrong? One from the right. So here's the right,
Oh, okay.
and here's the left.
So when it says it's approaching from the right, that means it's moving from the right to the left?
Yeah, from the right. If you're going from the right, you must be going to the left, right?
Thank you.
So as this guy said, you know, south winds of whatever. All right, wait a sec. Are the winds blowing south or are they from the south? Right? I had to go and Google it, and I think it's from the, but, you know, why not just say winds from the south, right? Or the north wind. I think that sort of says it's coming from the north. And, yeah, so that's why I sort of say from above and below, like above. Yeah, so. Okay. Algebraically determining. Yeah, we don't always have these graphing things this way, right? We never have these graphing things. So, you know, feel free to use them at home, though. It's handy at home, right? Like when you're doing stuff and you just want to, you know, you want to visualize it. I don't visualize with beans, but Desmos visualizes very well for me, right? And you can see stuff. Okay, algebraically determining the limits given the equation. The function is continuous. Okay, so case one, f of x. Remember f of x, function was continuous at the particular value of x. The graph of f of x, x squared minus 2x plus 3, is a continuous curve. In this example, f of 2 exists, the limit as x approaches 2 of f of x exists, and the limit as x approaches 2 of f of x is equal to f of 2, right? Since it exists, it's just the value that you evaluate the function, right? So that's on a continuous curve. It can be shown that if f of x is continuous at x equals a, then the limit as x approaches a of f of x is equal to f of a, right? Just as if it exists, then you just evaluate it at that value, boom, done. So example, determine the limit as x approaches 5 of this. Okay, so we can say, did I graph this? I don't know. I sort of threw everything in the grapher, so. There it is. So we're going for 5. And we can see that at 5, yeah, okay. There was a number there.
0.8.
0.8, exactly, right? But we gotta do this algebraically. So all we're gonna do is just say, hey, there's no problem at 5, right? There's a problem where? Like a negative 5 halves, there's a problem. 5 is not a problem. So all we do is substitute in 5. So we simply go equals, so it's going to be 5 squared minus 2 times 5 minus 3 over 2 times 5 plus 5, which is 25 minus 10 minus 3 over 15, which is divisible by 3. Let's go with 4/5, which was 0. We saw it. I don't know how much arithmetic you want to see when, you know, we're kind of working out stuff, but if I don't show enough detail for you, let me know, right? So if you're just saying, whoa, hang on, like how'd you get from there to there? Okay. And same thing for you guys when you're doing work, right? Like, you know, show enough. It shouldn't be where I'm looking going, huh? Like, how did you get, you know? It's not like you plugged it in your calculator, but it's, you know, show enough detail, right? The function is not continuous at a particular value, but if you evaluate it, you get 0 over 0. So remember g of x? G of x evaluated to 0 over 0, and it had a limit. So for g of x, x squared minus 2x plus 2, when determining g of 2, we got the expression 0 over 0. Although g of 2 does not exist, the limit does exist. How do we algebraically determine the limit? So sometimes factoring, or rationalizing the expression. And that might mean rationalizing the numerator, not the denominator, right? So that's why we did that rationalizing stuff, and the rationalizing the numerator. All right, so let's factor it, right? Because we know what's going to happen. It's going to cancel. So we're going to get an x minus 2 and an x minus 1, x squared minus 1 minus 2 minus 3. Always check. When you factor, you check. Okay, must. Over x minus 2. Okay. Zing, zing. So we say its limit as x approaches 2 of, and then we factor it. We cancel anything. We say it's the limit as x approaches 2 of, and now we have an expression which we can evaluate, right, by plugging in the number 2 and getting the value 1. Okay? But the limit stays on there until we're ready to stick the 2 in there. And we're not ready to stick the 2 in there until we have something that will evaluate to not 0 over 0, right? We want something that evaluates. Okay, good? Perfect. Examples. All right, now I got to remember I need room for this one, so I'm going to squeeze these guys on. Determine the limit as x approaches -3. Okay, so first thing we want to do is we want to evaluate this, right? You put a -3 in here, you get a 0. We get 18 minus 21 plus 3, which is a 0. So this will evaluate to 0 over 0, which means that it has a limit, and we're going to figure it out by, obviously, factoring, right? There's nothing else we can do. So we're going to start off by saying the limit equals the limit as x approaches -3 of, okay, now we're going to factor this, so 2x, x. Okay, so I know that's x plus 3, right? Because those have to cancel, right? Otherwise, I don't know, somebody messed up. So this got to be a 1. So 2x squared, 6, 7, yeah, okay. So it does factor, right? Verify it. Don't just say, oh, this has to cancel, and then it doesn't, and then, you know. So you verify, right? And you cross these guys off. So that's the limit as x approaches -3 of 2x plus 1. Okay, must say the limit as, right? Now we're ready to substitute. So that's 2 times -3 plus 1, which is -6. That's way too much information. I'm sure we all could have made the leap from 2 times -3 plus 1 to -5, but you don't need to show. Okay, did I graph that? 2x squared? I did, look at that. I think I just put everything in. And what were we approaching? -3. Well, okay, -3. Okay, I think that's pretty obvious, right? Scale's a half. Anyway. I always get messed up the first time I look at it because I think it's 1, 2, no, wait. Okay, -2 cubed is -8 plus 8 is 0. -2 squared is 4 minus 4 is 0. This evaluates to 0 over 0. Therefore, it has a limit. And we're going to factor. So it's going to be the limit as x approaches -2. Okay, do you remember how to factor a sum of cubes? I don't either. I just do it from first principles all the time. So you could memorize this stuff, but what do I need here? Plus 4. Okay, that's going to be an x cubed plus 4x plus 2x squared. So I'm going to need a minus 2x squared. So it's
minus 2x.
Yeah, minus 2x plus 4. Okay, so check that out. I do kind of, so I go x cubed minus 2x squared plus 2x squared plus 4x minus 4x plus 8. Right? Like I don't do a FOIL type thing or that. I do it like one at a time just because they're going to pair up and cancel if I do that. Okay, over x plus 2, x minus 2. Okay, these guys cancel. See what's left? Now look, I put a -2 in here, I'm good. Right? Put a -2 in here, I'm not so good. So now, what do we do? We'll just write the simplified form of x squared minus 2x plus 4 equals, now we'll put in the -2. And what do we got? We got 4 plus 4 plus 4, which is 12 over -4, which is -3. Okay, we'll look at it. approaching? Okay, -2, -3. -2 from below, so your -2 is undefined, but on either side is negative. Determine the limit as x approaches 2. Okay, so you put a 2 in there. You get 2 plus 7 is 9. √9 is 3, minus 3 is 0. And 2 in here, 0. Okay, we got 0 over 0, so there will be a limit. Now, all we can do here is rationalize the numerator, right? The only thing you can do here. You can't factor that. That's not factorable. So, I have left lots of room this year. So what am I multiplying by? Plus 3, right? The conjugate. Okay, so the top's actually going to be easy, right? It's just the first term squared, which is x plus 7, minus the last term squared, which is 9. Right? So it's going to be x plus 7 minus 9. And the bottom is just going to be this ugly mess. Okay, so what do we do next? What's x plus 7 minus 9? X minus 2. So, any huge objections if I just sort of cross this off and cross this off? Without writing down explicitly the x minus 2. I mean, we can see it's going to be x minus 2, so yeah, it's going to cancel. If not, do another line, make that an x minus 2, cross them off. Okay, so it's the limit. This last time we're going to write limit. That's of 1 over x plus 7 plus 3, and that's 2. Which is 1 over the root of 2 plus 7 plus 3, which is 1/6. What was it approaching? 2, right? 2. Wow, interesting curve, isn't it? Just sort of very gentle. You see the 0.167, right? What's 1/6? You know, it's 0.166 repeating. So you can do these algebraically, right? And then you can graph it, and then you can just, you know, drag it along and just see it. You know, sometimes it's nice. Okay, next page for you, but still the same page for me. Okay, what are we going to do? Well, we have a difference of cubes, right? We got something cubed. It happens to be a 4 plus 8. Yep. Okay. And we got a 64, which is the cube of 4. So, what do? We factor difference of cubes, right? Well, limit. So what is that? It's 4 plus h. Okay, that's the cube root of that. Minus 4. Actually, let's just hang on. Let's clean that up a bit. So 4 plus h minus 4. And then we have the trinomial, right? So that's going to be a plus 16. That's going to be a 4 plus h squared. And then we've got 4 times 4 times 4 plus h. over h. So if you want, could you just go to a piece of scrap paper and just do like x cubed minus 64? Right, and then everywhere you see an x, you're going to put in the 4 plus h. Okay, good. Oh, sorry. Yeah, you know what I said. If you want to, do a simpler one first, right? Take a piece of scrap paper, just do x cubed minus 64, and then wherever you see the x, put in the 4 plus h. Okay, so what do we got here? 4 plus h minus 4 is an h. So this is going to take out this. Right? 4 plus h minus 4 is h. That's one of the factors. And there's an h on the bottom, also factors. Just take them out. Okay. And then what are we left with? We got 4 plus h squared plus 4 times 4 plus h plus 16. Okay, well, I could put a 0 in there, right? It's okay to put 0 in there now, right? What we've done, we've gotten rid of the denominator. That's the thing that couldn't be 0. So it's factored out. So now, substitute. So we get 4 squared plus 16 plus 16, which is 48. I graph that. We'll have to zoom out if we want to see it, right? Filling that in. Now I had to do it with an X, right? I didn't have, but it's easier to do with an X. Right over here. There it is. Okay. There we go. So 0 undefined, right? But 46, 46, 47, 47, 48, 49, 48. I can restore that, right? There we go. Okay, let's turn that off. Okay, hey, fun times. Fractions. Everybody loves fractions. The limit as h approaches 0 of 1 over 2h plus 1 over h. Okay. Actually, complex fractions are much more fun than regular fractions, right? So here's what we're going to do. I think it's easier if we just kind of split this out and write it as 1 over 2h minus 1 plus 1 times 1 over h. Right? So instead of dividing by h, let's multiply by 1 over h, right? Okay. So this, actually let's put that brackets around that, right? Because it is the whole numerator that's being divided by h or multiplied by 1 over h. Okay, need a common denominator, right? Which will be 2h minus 1. So the 1 is already over 2h minus 1, so that's good. Plus, now that 1, to put it over 2h minus 1, I'm going to have to multiply it by 2h minus 1. So it's going to be 1 plus 2h minus 1. Now, there's not a whole lot of room here. 1 minus 1 is 0, right? The h on the bottom is going to take out the h with the 2. So that's just going to be a 2. That's going to be a 1. Okay. Now we're free to substitute, right? Because no harm 2h minus 1 if h is 0. So that's equal to, and that should be equals here too. Sloppy. So that's equal to 2 over 2 times 0 minus 1, which is what? Negative 2? 2. Negative 2. Show me a picture. Which one is it? This one. And what were we doing? What were we approaching? Approaching 0. Now, this doesn't look so good. Something's messed up here. What? Yeah? So as h approaches 0? Oh, right. Do this. Yeah, I'm looking here. But it's going to infinity. Yeah, or... What's it going to say next?
That depends how low you go.
Yeah, I know, like, there, undefined. But where is it? It's a negative 2, right? It's approaching negative 2. Okay. What if? So h of x, right? When f of a was equal to k over 0. For h of x, 3 over, when determining h, we have expression 3 over 0. In this case, the limit does not exist. Okay? Limit does not exist. So example, determine the limit as x approaches negative 1. So what do? We're going to throw a negative 1 in there, right? Just to see. So negative 1 minus 1 is negative 2. Negative 1 quantity squared is 1, minus 1 is 0. This evaluates to negative 2 over 0. So we say the limit as x approaches negative 1 of x minus 1 over x squared minus 1 does not exist. So what do we expect to see? I didn't put that one in there. I put that one in there. Something like that, right? Okay, wow, done. In summary, when determining the limit as x approaches a of f of x, three cases, right? If f of x is continuous at x equals a, then the limit as x approaches a of f of x is equal to f of a. So if it's continuous, stick it in there, evaluate it, done. Right? Stated. If f of x is not continuous at x equals a, but you evaluate f of a and you say, hey, this is 0 over 0, then you change the expression by factoring, by rationalizing the denominator or the numerator, or by simplifying, and then substitute x equals a. Now, basically what you got to do, you got to get rid of that denominator which is going to evaluate to 0 somehow, right? So you can factor it. That if it's that root x plus 7, you say, okay, I got to rationalize the numerator, which then hopefully will be equal to the denominator, right? That's the aim. And then they'll cancel, and then I can evaluate it. And if f of x is not continuous at x equals a, and f of a equals k over 0, then the limit does not exist. Okay? And you don't have to worry about trying to figure out the one-sided limits. Like at that point on the test, just you say, look, it doesn't exist. You just say it does not exist. Properties of limits. Suppose that the limits x approaches a of f of x and limit of x approaches a of g of x both exist and that c is a constant. Then the limit of f of x plus g of x is so the limit of the sum of two functions is the same as the sum of the individual limits. The limit of the difference of two functions is the same as the difference of the individual limits. This is they're all in your textbook. I'm going to let you fill that one. And basically just the c comes out front. So it's equal to, if there's a constant, then it's the constant times the limit as x approaches a of f of x. Okay, so in other words, you see a constant, you just throw the constant in front, work out the limit, multiply it by the constant. The limit of a product is equal to the product of the individual limits. The limit of a quotient is equal to the limit of the individual quotients, providing that this is not 0, right? If that's 0, then. The limit of a function raised to a power would be the same as the limit as x approaches a So you can raise the function to the power and do the limit, but it's a lot easier to do the limit of the function and then raise it to the power. Okay. And the old nth root of the thing says you can probably do what? Okay, you do the limit as x approaches a. Oh, sorry, actually, you can do the nth root of the limit. Okay, I'm pretty sure all this is in your, there's a page, I think it's 38 rings a bell, but that might be wrong. In your brand new books. Yeah, it's not 38. All right, questions?